Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel. And in today's video we are going to approach to the second part of our double integral that deals with the iterated integration over a rectangular region, so explained by an Italian mathematician, Guido Fubini. I don't know how to pronounce this Italian name. It could be a Guido or Guido, whatever it is. So this was the Italian mathematician having this period, and he asserted a theorem related to the iterated integration in 1907. That was the period. Okay, so this was the time when he just presented this theorem related to the iterated integration over rectangular regions. Also, he presented the same theorem related to the non-rectangular regions, or you can say it irregular regions, but this is not the part of this video. We are going to cover that thing in the next part, means the part 3 of our video is going to be going to deal that situation. So over here we are going to focus that how iterated integration or double integrals are going to be applied over rectangular regions. So what this Fubini stated related to this stuff. So here you go, the theorem. Okay, so here you go, the theorem, and this Fubini stated that if you're having a certain function, a bivariate function, which is continuous over a rectangular region G. So, and here the rectangular region lying on xy plane is restricted by means of these boundaries, means x value is lying within this closed interval AB, and y values, the y coordinate of each point, I must say, it belongs to a closed interval CD. So over here I have just maintained here, I just tried to maintain here a rectangular region G lying on the xy plane, you can see. And this is, for example, your G. That's the rectangular region. And on the x, on the value on the x coordinates present entirely in this region, all the points, the x coordinates of all the ordered pairs which are lying on this plane G, they are restricted within this closed interval AB on the x-axis. Okay, and the y coordinates of all the points lying on this plane, they are restricted by C and D. Okay, so this is the C point, this is the D point, and that's what this region is entirely restricted about. So also you can write like this, that your x points or x coordinates, they all belong to this closed interval AB, and your y coordinates of all the points, they belong to this closed interval CD. There could be any real numbers where AB and CD, they all belong to your real numbers. That's it. Okay, so now what exactly this double integral states, I told you already in the part 1 of this series, that once if you are having a well-defined bivariate function f of xy, which is having the value other than 1, or it is expressed by means of some algebraic expression, then this double integral is actually explaining you a volume bounded by a certain surface S, which is lying right above this G. That's what I tried to explain in the first part of this video. You can see in the description box. So exactly over this region, if I just try to maintain here a surface S, which is similar to this region, but it's lying in the 3D coordinate space, 3D space, I'm going to maintain here an object which is having the bottom G and having the upper surface explained by means of S, which is exactly similar or exactly congruent to this plane G. So the volume of that object is going to be explained very firmly by this double integral. Okay, but that's what the Guido Fubini tells, that how you're going to maintain, or how you're going to evaluate, or how you are going to perform this double integration in order to find out the volume. okay, bounded by the certain surface S and this plane G. So let me maintain here surface S and let me draw here a 3D object, okay. Okay, here I just tried to maintain here a certain surface S maintained by this green color right above this G, and I just call this surface as my S, which is expressed by means of a certain function capital F, and here Z is another function which is actually your small f of xy. Okay, this is your surface S lying in a 3D space right above this G. So we just maintain here an object bounded by the surface S and the plane G. So our objective is to find out the volume of this 3D object. Okay, so the Fubini states that you can find out the volume of this object by performing an iterated integral or iterated integration of this double integral. Over here you can see that this function, this integration, this integral representation bounded by a certain plane G and having a certain function f of xy, you are having a certain 3D object volume. So you see here the integral limits of your x-axis and your y-axis is expressed over here like this, and d of x, dx and dy are the product of these two differentials gives you actually the area. So you can write dx dy by means of simply dA, it doesn't make any difference. So if you are planning to integrate your this bivariate function keeping your y fixed, or keeping your y as a constant, or simply assuming y as a constant, and you integrate your bivariate function by means of your x, then you are going to simplify, or you are going to exercise on this integral first. You apply the integral, you apply the limits after obtaining the integral function, and then whatever the answer you're going to get, after that you're going to integrate that thing with respect to y, and then you apply the subjective integral limits. Okay, this is the first way. Another way is that if you keep your x variable as a constant and you integrate this function by means of your y, then you are going to perform these integral limits first, which are the integral limits of your y variable, and whatever the answer you get, it is definitely going to be in the form of some algebraic expression involving x variable, and then you just integrate that thing with respect to your x, and then you apply the corresponding integral limits representing the range of your representing the boundary of your x-axis. So that's how you just perform the iterated integration in two ways according to Fubini. And one thing more, the mandatory condition is that the function f of xy should be continuous throughout this plane G, and that's a very only in that case it is going to be integrable. That's the major requirement of this entire theorem. So now we are going to move on, and let's have a look to the example. And before approaching to the example, keep this thing in mind, as I have already discussed this thing in my previous part 1 of this video, that if your integrand is equal to 1, then this integral is going to explain you simply the area of this plane G. Okay, but if you're having a certain algebraic expression at the place of this integrand, a well-defined function algebraically, then when you evaluate this entire double integral, you are going to have the volume bounded by this surface and this plane G. Okay, so let's have a look to the example. Okay, so here you go, the example. Here you can see that in the question, this differential of x is mentioned first. So the integral which is written along with this integrand is actually explaining you the limits of your x-axis. Okay, So we are going to identify that which integral, because both the limits are expressed in the number form. So how we are going to identify that which integral is representing the x representing x and which integral is representing y. So we are going to understand this thing after examining or after analyzing this setup. Here d of x is written first, so this integral is representing the integral with respect to x, and obviously the next integral is going to be representing the integral with respect to y. So first of all, what we do, we are going to integrate this bivariate function with respect to x. Then we apply the limits. We are going to get some answer which is going to behave as the integrand for this integral, and then we are going to integrate it with respect to our y, and finally we apply these two limits, and that is going to be the volume of the subjective 3D object bounded by a certain surface and this plane G. Okay, I just try to maintain here plane G having on this xy plane. This is the G having your y values from 1 to 2 and x values from 0 to 3. Okay, it's going from 0 to 3 and y values going from 1 to 2. So this is going to be my rectangular region, and the surface which is going to explain here by means of a certain function x, y, and z, and here z is actually my integrand function, which is my x plus y. Okay, so I just try to I'm going to draw here a surface S, possibly explaining how it looks like once when it is plotted according to this format. So here it is. So that's how a surface could possibly looks like. Okay, and right above this G, and now we are going to bound and we are going to sketch an object bounded by this surface and this plane G, and then we are going to find out what could be the volume of that object, and this integral is going to help us out. Okay, so let's see, let us draw the height of this object. So here you go. It's just an idea how a thing could look like, and that's it. It's not a very according to scale, but I just try to sketch it in order to get an idea, and that's it. So we have to find out the volume of this 3D object. Okay, so here you go. Now I'm going to integrate now this integrand, keeping y fixed, and I'm going to integrate it with respect to my x. Okay, here you can suppose that your y is just a constant number. Okay, you're going to just assume it like this. So I just maintain here a bracket. I'm going to perform my integration here. Divide outside. All right, so that's what a volume is. Okay, sorry, it's one. So you're just going to apply here the basic integration formulas, no need to repeat that. This is a constant, so it actually is written something outside. So this thing gives you x, so let us write it along with it. Also, you can keep your y outside, it's your choice. Okay, so that's it. Now let us apply the limits 0, 3 in these two functions that we have just obtained. It's going to be 3 square upon 2 minus 0 square upon 2. you always apply your upper limit first. Second fundamental theorem of calculus, we have studied that. 0 into y, it gives you y, but I have to be very precise, so I'm just mentioning that. So this thing is giving you 9 upon 2, and this is giving you just 3y. And now you can see that we are having an answer that we by integrating this integrand with respect to x, we are having this thing, and now this is going to behave with an integrand for this integral, and we are going to evaluate it keeping with respect to our y. We are going to integrate it with respect to our y. So quite sufficient space. Let's continue from here. So the volume is equal to 1 to 2, and 9 upon 2 is a constant number, so we will write just outside, and we apply our differential here, and 3 is outside. Every time I write 0 here, it's just an habit, sorry for that. Okay, that's it. So now the integral of your one integrand gives you the corresponding variable mentioned in the differential. So it's nothing but y plus 3 times y square upon 2, 1 upon 1 and 2. Okay, let's apply the limits. Two is square is 4, minus 1 is square is 1. Okay, now page is really exhausted. Let's manage another one. So the volume is therefore 9 upon 2 into 1 plus 3 by 2. That's simply a basic thing now. You just have to perform some arithmetic rules, and that's it. You take out the LCM of this stuff, and it becomes, sorry, it's 2. 9 plus 9 is 18 upon 2. It gives you 9 cubic units, because as it's a volume, that's why the unit is expressed in cubes. So the answer is 9. So 9 is actually the volume of this 3D object bounded by this surface and this plane G on the XY plane. So that's how you find out the volume, and in the same way you can perform the same integration keeping y fixed. Manage over here. Now this time I'm going to integrate my same function with respect to y first, keeping this integral in front. So I'm just going to perform the same, I'm going to exercise on the same question. So this time I will integrate this integrand with respect to y, so I will just swap my integrals, and I will write it like this. Okay. And I will swap my differentials as well, like this. Okay. It is actually nothing but volume, as I have said already before. So now, once again, that's what we are doing. So x is a constant stuff right now, so simply it is written outside the integral. It's like this. So over here you're going to have nothing but y and over here you're having y squared upon 2. Then you apply the limits. That's it. So when you apply the limits, it gives you x times 2 minus 1 plus 1 upon 2 outside. The square of 2 gives you 4, square of 1 gives you 1, and that's it. So this thing gives you simply 1, so over here I simply write my x, and over here I will write my 3 upon 2. So now the integrand that I'm having, that I'm going to integrate with respect to my x, is this. Okay, so let's do it. 3 upon 2 is a constant number and an outside, and that's it. So it gives you x squared upon 2, 0, 3, plus 3 upon 2 times x, 0, 3. Okay, that's it. Now let's apply the limits carefully. It should give me the same value 9 at the end. So it gives you 3 square upon 2 minus 0 square upon 2. Okay, plus 3 upon 2, and it gives you nothing but 3 minus 0. Okay, so it is 9 by 2 plus 9 by 2, and you can see that you are having exactly the same value, units cube or cubic units, whatever you want to write. So same answer you're having if you just perform with respect to, if you integrate the integrand with respect to x first or with the y first. You just have to be careful, and you have to swap the integrals if you want to integrate in a different way. So always remember, the integral written first is representing the range of this variable mentioned with in the first differential. Okay, so if you want to perform the integration with respect to this variable, then you have to swap the integral, you have to bring this integral first, and so on. So that's what your Fubini states regarding the iterated integration on a rectangular region. So that's all for today, and in the next video we are going to discuss the same theorem over non-rectangular regions or irregular regions. Okay, if you find this video helpful, I humbly request you to subscribe my channel, hit on the like, share this video with the other learners, and don't forget to hit on the bell icon for the latest updates. And also, I appreciate if you just put down your feedback in the comment box. And if you have any queries and questions related to the mathematics, you can ask for me, and I'll be honored if I just put down some proper enunciations and explanation related to that. Take good care of yourself. Allah Hafiz.